Hello, everyone, and thank you for joining us today. Before we get started, I want to point out a few things. On your control panel, you'll see options for chat or questions, and please use those tools to communicate with us if you experience any issues during our presentation, or if you'd like to submit a question, which we'll be reviewing at the end. If you would please go ahead and send me a quick hello so we can make sure everything is working. Okay, thanks, guys. See a couple of you said hello. So if you, again, have any questions, we'll be reviewing those at the end, so you can go ahead and submit them throughout, or you can hold them for the final presentation slide where Matt will ask for questions at that point. And other than that, I'll go ahead and introduce Matt today. He has nearly 30 years of process engineering and project management experience. Matt has been published multiple times in magazines and is an internationally recognized expert on combustible dust and related regulations. He's led projects for several clients to conduct post-disaster explosion investigations, implement plant recovery strategies, develop process safety management redesigns, and develop facility PSM policies and procedures. As ADF's engineering manager, Matt leads a team of engineers on a variety of process development and improvement projects in the food, feed, bioscience, and consumer products industries. He earned a degree in chemical engineering from the University of Kentucky, is a licensed professional engineer, and is a member of the American Oil Chemists Society. So with that, I will turn it over to Matt and let him get started.
Okay, thank you, Courtney. This presentation is really about how to conduct a dust hazard analysis. At this point, I'm assuming that you understand what a dust hazard analysis is and what is required. So we'll go through that briefly. This all started in September of 2015, 3 years ago, when NFPA issued the new standard on fundamentals of combustible dust called NFPA, which is NFPA 652, which established a relationship overarching of all of the standards that had existed before. And those were standards that you would be familiar with, such as NFPA 61, 654, 68, 69, and several others that cover a variety of different industries. The one new thing that 652 created that didn't really exist before was the rule requiring a dust hazard analysis. A dust hazard analysis, of course, this is like a PHA, similar but different in that it is focused primarily on the dust hazards. This is required for all facilities that generate, process, handle, store combustible dust. Is not specific to any one industry, but is also retroactive. No matter how old your facility is, you need to have a DHA in place. Now, when the original standard was issued in 2015, they set a 3-year timeline for everyone to come out with their DHAs. Well, that was fairly aggressive, and the people on the committee for NFPA, and I know some of them, felt that recognized that this was a bit aggressive, and of course not everyone was able to make September 2018. So in the update to the standard just last month, came out with an update to the 652 standard that moves the date out to September 2020. So you've got a couple more years now to get your DHA in place. What's in a DHA? A DHA, first of all, needs to include all of your combustible dust data. That's all of the information that relates to the combustibility of your material. How much of a detonation can it produce? How sensitive is it? and so forth. Identification of different areas of risk, credible ignition sources, suspension mechanisms, operating ranges, protection methods, propagation hazards. These are the things that you need to explore within the DHA. And I'll talk about each one of these. First, there was a video that I found that is very telling of what can occur even outdoors, where normally in a combustible dust scenario, you look for the normal fire triangle plus a couple of other things. One is containment and the other is dispersion. And the point here is even without the containment, you can still have a flash fire that is highly hazardous. And this is a video of a facility in Indiana that was just transloading corn. And you see the silo over the truck loadout building here that is already collapsing. And so the key thing here is this is outdoor. And there's a person videotaping this who probably didn't realize what a hazardous situation that he put himself in. But as you'll see here, in the video, the silo starting to collapse and corn starting to spill out the top. You'll see it come out the other side. There it is. And in a moment, the silo itself the bin will completely collapse. And watch what happens. There it goes. And boom. And certainly if the person filming that on his phone had any idea what was about to happen, he wouldn't have been there doing it. But the other point of this is if this had occurred inside of an enclosed building, that would have been an explosion that would likely have killed the person filming this. And that's part of what's driving this sort of thing. So the first step in defining your DHA is to define your dust. You need to understand what dust you have, what type of dust they are, how much of those dusts you handle, how much are your personnel exposed to, are there dust clouds produced during your production process at any point. You need to outline your hazards, conduct a DHA review meeting. Now this is a meeting on site where you have a number of people involved who review item by item, step by step, the hazards throughout the facility, much as you would do with a PHA. You need to prioritize those hazards, create an implementation plan. And it's that implementation plan that you need to have in place by 2020. That's the actual requirement. Finally, you need to design and implement those solutions according to the implementation plan that you developed yourself. So if your facility is audited by OSHA, and they are doing random inspections for this, but it's highly prioritized towards certain industries. But if your facility is audited for this, what they're going to be looking for is, do you have an implementation plan in place, and are you following the timeline and the steps of the implementation plan that you wrote yourself? So they're holding you to it. And they're holding you to this based on the general duty clause. So first of all, in defining your dust, the primary thing you need to do in identifying your dust, focus on the greater hazard. So if you're dealing with hundreds of materials that may be combustible, it's impractical for you to go out and test every dust. It just can't be done. What you'll want to do is sort those dusts into categories, types of materials, and then you'll want to identify the ones that are greater hazard, that have smaller particle size, that are drier materials, that present the greater hazard, and then you'll hold your facility to those worst case hazards. One thing you'll need to do if you do not have your combustible dust data is that you may have to test this material. And there are a number of testing labs that are available that do this type of thing. They generally require about 2 liters of material to be able to do a full battery of testing. And you'll find that this costs anywhere from $3,200 to $4,000 a sample. So if you've got a lot of samples, that adds up to quite a bit very, very quickly. So you want a good idea of what materials are the worst case that you'll want to hold your site to. Also keep in mind, another of the requirements of NFPA 652 is that anyone who is producing and selling materials that would be considered combustible dust must put on the SDS that goes out with shipping that material, the combustible dust data. You'll need to see the KST, the MEC, and the MIE at a minimum on those on the SDSs, which means if you're bringing in a lot of raw materials yourself, you may lean on your supplier to get you that data, and that can go a long way. The other thing to keep in mind is you don't necessarily want to trust data straight out of literature, off the internet, because you're betting that someone else's dust is going to behave exactly like the dust you generate on your site. If you're bringing it in as a raw material and it's a common thing like soybeans and corn, in that case, literature data is probably fine. But if you are grinding those materials with your own mills and concentrating that up in dust collectors, you'll want to test your own material because you can't trust the data from the literature to match your material. It may not have the same moisture content, it may not have the same particle size distribution, so it may not be the same. What's more, you really want to have, especially if you're looking at a packaging situation, you may want to have your dust tested as received rather than having the lab grind and dry that material, because if you don't tell them to do it as received, they will grind it and dry it, which means that they're going to try and concentrate up those dusts themselves, which will make it a worse case than you may actually have in the field. If you cannot get your samples from a dust collector, that may be the right thing to do, because you don't know how dangerous the material is in your dust collector based on what you may be packaging. But if you want to know how hazardous the material is at your packaging line, then have them tested as received. And the first thing that they will do is a go, no-go analysis. And that may tell you right there that they may not be able to make it combust as received, in which case you have a no-go analysis, and that's the paperwork that you need to show to OSHA to say, hey, my dust is not combustible in the condition that it exists. Maybe it's not fine enough or it's too high a moisture content, in which case you will need to do nothing as far as an implementation plan. So what are some of the data that you'll need to collect? First of all, the first group of testing revolves around the KST, and this is a term you may have heard of. KST is a calculated measure of the severity of an explosion that can be generated by your material. And it's defined as the rate of pressure rise over a given volume. That rate of pressure rise is also a bit of data that is useful, but it's mostly useful to those vendors who are out there designing equipment like explosion panels and the suppression and isolation bottles. They need to know the speed at which they have to respond, and that comes from that rate of pressure rise. The other data point you'll get with this is the Pmax, which is the maximum pressure that can be developed by an explosion. One of your options in designing vessels is to design that to contain that maximum pressure. That's impractical for many industries. For a grain bin, for example, you would never do that. You're looking to design vessels at 150 psi. That's just impractical. If you're in the chemical industry, the oil and gas industry, that may be more practical. Other testing that you will need that I certainly would recommend, one is the MEC, the minimum explosible concentration. This tells you how much dust you need in a given volume before you need to worry about the potential for an explosion, because another option you have is to operate below the minimum explosible concentration. That's like handling a flammable liquid where you want to run below the LEL of a vapor. It operates in much the same way. You can operate below the minimum explosible concentration, and that's a way to deal with it. MIE is critical. That's your minimum ignition energy. That defines how sensitive your dusts are to ignition. And the lower the value, the worse it is. When you get below 50 millijoules, a number of additional requirements come into play from the standards. And actually, a human spark is generally about 30 millijoules, 25 to 30. But NFPA 77, which defines the requirements for static electricity, come into play whenever you go below 50 millijoules. That'll determine the bonding and grounding needs in your facility. When you get down below 25 millijoules, you have a very, very sensitive material, and the requirements go up quite a bit, particularly in terms of electrical area classification and in grounding and bonding. You also, at this point, need to get into grounding your personnel who may be handling the material. So if you're packaging a material that has an ignition energy down around 10 millijoules, you're going to have to ground the personnel to the equipment with things like static dissipative flooring, static dissipative footwear, or grounding straps on the wrists. The other one that I recommend, minimum ignition temperature for a dust layer in particular, that is the temperature at which the material will auto-ignite. So if you're settling material on light fixtures and motors, this determines how hot you're allowed to get that equipment, which goes into the electrical insulation specifications. You may have a T3 motor requirement as opposed to a T4 or or a T1. So you can't allow that motor to get hotter than that minimum ignition temperature. Minimum ignition temperature for a dust cloud, that is something that if you're putting this material into a spray dryer, you may need to know that because if you're bringing gases in that could be higher than that ignition temperature, you could have another issue inside your spray dryer. So here's a table that I believe they've removed this now, but this was in NFPA 68, where a lot of the design requirements for combustible dust existed. And what I want to point out in this particular table is that you'll see the source down at the bottom. This came from the U.S. Bureau of Mines in 1961. So these are grains. What does the U.S. Bureau of Mines know about your grains and the grains in your facility? And I guarantee you from 1961, this data is no longer valid. This was tested in a different way with a different test method. The tests have changed. So this data is invalid. And this is just to point out the dangers of trusting that data that you'll find out there in literature. So the next step in your DHA process is to outline the hazards that you have. You need to define the different nodes throughout your facility, the paths of travel of an explosion. So if you have an explosion in a dust collector, do you have an open pathway to another piece of equipment where nothing would stop that propagation of that explosion to the next piece of equipment where you'll have secondary explosions? It's those secondary explosions that create the bigger hazard. Identify your existing protection and isolation equipment. make sure that it's adequate, and importantly, measure the indoor dust accumulations that you have to make sure that and identify those areas where you may be identifying higher levels of dust on the floors, on the rafters, on lights, and so forth. Then you conduct your DHA, including such participants as the site safety manager, site engineer, operations, people who are familiar with the site and the way operations looks at all periods of time. You may find that 99% of the time you don't have dust clouds in the room, but the operators or the people who are doing the cleaning, they recognize that under certain conditions, a dust cloud can be generated. So that needs to be pointed out. You need to review each of those nodes primarily for the likelihood of an event. The one thing that makes a DHA different than a PHA is that in a PHA, you're going to look at the likelihood, the severity, and your detectability. In this case, the severity is pretty much going to be the same no matter what. It's really going to boil down to the likelihood of an event, which means do you have all 5 sides of the explosion pentagram? You need to document these recommendations and their likelihood to spread to other parts of the facility. So I know you can't read this, but this is just kind of an idea of what a finished DHA spreadsheet looks like. That's the one that we use. And in the middle of that, you see that likelihood column. That's the one you'll want to follow in terms of setting your priorities. Finally, based on that DHA, you'll put together a written implementation plan to address those risks. Identify responsible individuals who own the mitigation plan, and you'll need specific dates. That's what OSHA is going to want on this. They want to see those specific dates because that's what they want to know. Are you holding to those specific dates? The plan, however, may include certain things like investigate further. We'll do a study on this. Things can be deferred in that way. One thing you want to do, conduct an engineering investigation of the systems in high-risk areas to determine the best way to do some of these things. So there are a lot of options that you have. You don't have to just immediately jump to explosion suppression or chemical isolation. These systems they're effective, but they're also expensive. And if you go straight to a vendor, there are a lot of very good, reputable vendors out there who make this equipment, but of course they're a vendor and they're very happy to sell you a bunch of suppression bottles, whether you need them or not. So by going to a neutral third party, such as a qualified engineering firm, you'll get some other ideas that may not involve some of this expensive equipment, such as the ability to operate below explosible concentration, the ability to operate above the PMAX, or to design your equipment above the PMAX. There are other ways to get around some of these things. Inerting is another option that is out there. Ways to redesign silos and vessels so that you can create explosion relief with weak roof designs rather than adding panels to the side, these kinds of things. You'll find most of these things outlined in NFPA 69. That's where the description is of all of the different types of implementation plans or different methods exist for explosion suppression, mitigation, and isolation. Of course, chemical suppression is certainly available. You see here a picture of an explosion suppression bottle. Flameless vents are another very good option if you have a dust collector or some other vessel indoors where you need to have an emergency vent, but you don't have the option to take it outside. Inerting, operating below the explosive concentration, these are some other things I mentioned. So engineered solutions are allowed. So if an engineer can come up with a less expensive way, all you have to do is document that, and the risk that remains after implementing that solution, you just document that, and that's acceptable. Isolation is something that comes up frequently at these DHAs, particularly around things like dust collectors. Keep in mind, rotary valves, rotary airlocks can act as isolation, but NFPA 69 calls out some very specific requirements around a rotary valve. For example, the clearances can only be 0.2 millimeters, and they must be hard-tipped with at least 6 veins, so that you always have 2 veins touching the wall at any given time. And you'll find that most rotary valves out there in industry do not meet that requirement. There are, however, some other pieces of equipment, for instance, passive isolation with flap valves that are fairly inexpensive and can be made in a very large size. And they're often the best way to go. The downside of it is you need a certain distance from the equipment, and you may not have enough straight ducting available to make passive isolation effective. So in conclusion, the first step is you need to characterize your dust. You need to understand what you have. You need to understand the risks, perform that DHA. And you need to have your implementation plan in place by September of 2020. And you need to follow that implementation plan. Keep in mind that these implementation plans do not necessarily have to be expensive. There are a lot of different ways to do this. So with that, if there are any questions, hand it over to Courtney.
Okay, thanks, Matt. Like you just said, if you have any questions, please go ahead and type those in right now while I get the screen pulled up, and we'll see what we've got. Okay, it looks like we have a couple here. What would be a price point for a DHA?
So it's going to depend on a couple of things. One is how many dusts are we talking about? Secondly is the size of your facility, is the size and complexity of the facility. And then the third thing is going to be how well documented is that facility. So if there's a lot of good documentation about the equipment that you have on site, it's much easier to develop that DHA, that implementation plan. If you need to generate a lot of that, it can get very complicated. So generally, you'll find a very small facility, maybe a little transload facility that's only dealing with one type of dust. You'll find DHAs easily less than 10,000. So 8 to 10,000 for the smallest facilities, up to the largest facilities. If you're dealing with a corn dry mill, or if you're dealing with even larger than that, if you're dealing with actually an oil seed plant can be even bigger than that in terms of the dust hazards. Particularly if you're doing a lot of dry milling, you'll find that those run upwards of 18 to 20,000.
Okay, thank you. Our next question is sugar considered an explosive dust? Absolutely.
I personally have done DHAs on sugar facilities. And sugar, as you may know if you're familiar with it, is a very, very friable material, especially when you're doing pneumatic conveying with sugar. You're going to find it breaks down into powdered sugar very, very easily. Sugar is actually what started NFPA 652 to begin with. It started with the Imperial Sugar Plant in South Carolina in 2008, where an explosion from sugar. It wasn't even powdered sugar, it was granular sugar. There was enough dust generated once they had enclosed a belt to wipe out the entire plant and caused 14 fatalities in that facility. That was a sugar facility. So not only is sugar an explosive dust, it's one of the dusts that OSHA is targeting. If you're running a sugar facility, you have a much higher chance of being randomly audited by OSHA. So keep that in mind.
Great. Okay, and looks like we only have one more question. So again, if you have any, get them in here now before we're finished. And the last question is, how many DHAs have you done?
Oh, boy, I have to stop and count. I've done quite a few this summer alone, because as I mentioned, that original deadline was this September. So for me, I spent the entire months of June and July and into August, even into August, doing DHAs. I think I did 7 this summer. And in the months before that, there were fewer, or they were less frequent, but I had done I'm sure it was at least half a dozen in the prior year. So I'm well over a dozen DHAs in the past 2 years.
Okay, thank you. Looks like that's all we have. And if you think of any questions after we close up here, Matt's email address is right up there on the screen, mwilliamson@adfengineering.com. Just go ahead and send him an email. And also, if you would like a copy of our PowerPoint presentation from this webinar, we'll be sending that out to everyone who attended as well. And I believe we are all done here. So thank you all for joining with us today. And we hope to hear from you soon. Thanks, and have a good afternoon.